Hello guys, welcome back to lecture series on Fourier transform. So in our today's video, I'm going to explain to you all one of the example which is very much important for our upcoming exam, okay, that we have to find out the following integral equation, okay. So whenever we have to find the integral equation, make sure that whether we have to apply Fourier sine, inverse Fourier sine transform or inverse Fourier cosine transform, okay. So based on this topic, I already uploaded plenty of the videos in my channel, guys, okay. So if you are interested to see this video, do check in my playlist, okay. So in our today's video, we go and learn this example, okay. Yes, so let's get start the solution. So as we have solved following integral equations, small f of x, integral over 0 to infinity, small f of x cos lambda x dx, okay, and it has a two piecewise function given, okay. And first piece, it says that whenever we have the value between 0 and 1, okay, included 0, included 1, okay, then we consider function 1 minus lambda, okay. And when we have lambda which is bigger than 1, we consider the function as a 0 only, okay. Yes. Now let's go for finding the integral, okay. But before finding this integral now, let me explain this interval, okay, with the real line, okay. Let me consider I have this real line over here, okay. This one is the real line, so it is a 0 all point, okay. So it goes here all the way to the negative infinity, it goes to the all the way to the positive infinity, okay. Yes. Now see that we have the piece for interval 0 to 1, okay, it is 1 over here, okay, 0 to 1, and another piece for the function, it is lambda bigger than 1, okay. That means whenever we have interval from 0 to 1, okay, lambda between 0 to 1, we consider 1 minus lambda as a given function, okay. Yes, so we consider 1 minus lambda, okay, 1 minus lambda as a given function between 0 to 1, okay. And whenever that interval exceed bigger than 1, that means over here, okay, to this side, okay. Yes, whenever that interval exceed bigger than 1, we consider the function as a 0 over here, okay. Yes, that means now see that we have the given value for. Now if you compare this with the Fourier cosine transform, so you will get these are the Fourier cosines values, okay, fc or fc lambda, okay. These are the values for Fourier cosine over lambda, okay. Yes, now let me write the formulas so you can easily identify how the function can be defined over here, okay. So we know that the Fourier cosine, okay, Fourier cosine transform over lambda, okay. What is the Fourier cosine transform over lambda? F suffix c, okay. I'm writing f suffix c over lambda can be written as integral over 0 to infinity small f of x cos lambda x dx, okay. This one is our required Fourier cosine transform, okay. So if you compare this one with our given example, if you compare this formula with our given example, it seems like that this side it is equivalent to this side, so both are equal here now. So these sides are equal, so obviously Fourier cosine over lambda, their value may be 1 minus lambda or it is a 0 for these piecewise functions, okay. So we have the two pieces of our intervals. Yes, so what are the possible value for Fourier cosine over lambda? Now see that, let me write these values here just for your conceptual clarity, okay. So Fourier cosine over lambda, okay, Fourier cosine over lambda, we take 1 minus lambda, okay. That means this is the value equivalent to this, that means this is equivalent to this, so Fourier cosine over lambda, which is 0, okay. Yes, now I hope you all have understood how I have written this one, Fourier cosine over lambda, okay. Yes, which is 1 minus lambda and one of it is 0, okay. So we have the partition for these two functions, okay, Fourier cosine function. So one it is partition over here and another in one here, okay. I define these pieces of the function over here, okay. Yes, so if you have given formula in the form of Fourier cosine over lambda, okay, and we have to solve the integral, and always remember that whenever you have to solve the integral now for Fourier cosine, Fourier sine, so always apply for solving this integral, always apply inverse Fourier cosine transform or inverse Fourier sine transform, okay. So as we have example in the form of cosine transform now, apply inverse Fourier cosine transform, okay. Apply, let me solve next part, apply inverse Fourier, okay, apply inverse Fourier cosine transform, okay, cosine transform, apply inverse Fourier cosine transform. Okay, so let's go for applying inverse Fourier cosine transform. Okay, fc of lambda and fc of lambda. Okay, so we have 1 minus lambda and 1 minus 0 here. Okay, so what is the formula for Fourier inverse Fourier cosine lambda over x? Okay, so we write a inverse Fourier cosine transform as a f of x, which is equal to 2 by pi. Okay, so the value for inverse Fourier cosine transform, it is a 2 by pi. Okay, yes, and integral over 0 to infinity. Okay, 2 by pi interval over 0 to infinity. Okay, so integral over 0 to infinity Fourier cosine. Okay, Fourier cosine over lambda, Fourier cosine over lambda. Okay, Fourier cosine over lambda, as we have Fourier cosine over lambda given. Okay, yes, we write cos lambda x. Now as we have Fourier cosine over lambda, so we have to take integration over d lambda. Okay, because we have the function in the form of lambda. Okay, and we are working on inverse Fourier cosine, so we are going to integrate our given function with respect to, as we have lambda, so we are going to replace integrate with the respect to d lambda. Okay, yes, now let me break this interval into the two pieces. Okay, as we have one piece over here, another piece here. Okay, so I'm going to break this interval. Okay, as this one is a standard property for breaking intervals. Okay, so 2 divided by pi as it is. Okay, so 0 to infinity can be broken by, okay, it is 0 to infinity can be break by 0 to 1 and 1 to infinity. Okay, so we write 0 to 1 integral over 0 to 1. Okay, so first interval, it is 0 to 1. Okay, that means 0 to 1 and 1 to infinity. Okay, 0 to 1 Fourier cosine over, yes, okay, Fourier cosine over lambda. Okay, Fourier cosine over lambda cos lambda x d lambda. Okay, yes, this one is our first integral, first broken integral. Okay, yes, and plus another integral, I'm going to break it as the 1 to infinity. Okay, integral over 1 to infinity, integral over 1 to infinity Fourier, okay, cosine over lambda. Okay, Fourier cosine over lambda cos lambda x d lambda. Okay, so bracket complete here. I hope you all have understood how I have written these two intervals. Okay, this is just a breaking of interval. Okay, as we have given two different piecewise functions, and always remember that whenever we have two different piecewise function, we have to break the intervals. Okay, yes. Now as we can see that whenever we have interval between 0 to 1, interval between 0 to 1, we consider Fourier cosine over lambda as 1 minus lambda. Okay, so replace this value here, 2 divided by pi, okay, under bracket 0 to 1. Okay, keep as it is, integral over 0 to 1. I'm not going to change that one here. Okay, Fourier cosine over lambda, which is a 1 minus lambda. Okay, Fourier cosine over lambda, which is 1 minus lambda, I replace here. Okay, cos lambda x, cos lambda x d lambda. Okay, yes, first bracket complete here, plus. Now second, we can see that whenever we have integral 1 to infinity, what we take, Fourier cosine over lambda 1 to infinity, Fourier cosine over lambda is 0. That means this value we consider here, and if it is 0 multiplied by cos any term, it gives us the 0, and integration of a 0, it goes to 0, so entire term gives us the value 0. Okay, so we don't have to take that next step. Okay, yes, we are going to deal this integration only here. Okay, so 2 by pi, it is a constant term, keep it outside. Okay, we are not putting this term while we are calculating this integration. Okay, yes. Now as we don't have any standard format for solving these two by functions, okay, as we have one algebraic function, second one is a trigonometric function. Okay, for solving these two function, we have to apply by-part rule for integration. Okay, by-part rule for integration. So what is the by-part rule for integration? It says that, now see that guys, there are two different by-part rules. Okay, there are two rules for finding the integration in the form of by-part. So I already explained both of the rules. Okay, so you can apply regular rule that you learn it in from your 12th standard and so on onward. Okay, so that means integration of u into v, which is the u into integration of v minus integration of derivative of u into integration of v. Okay, that you can apply. Okay, or and recently I introduced one more integration result. Okay, yes. Now see that I'm going to find this integral over here. Okay, this integral I'm going to find it separately. Okay, keep this one, we are going to put this value over here. Okay, so find out this integral, substitute here, apply over limit 0 to 1. Okay, yes. So for finding this integral, I'm going to explain to you all one of the pi part rule for finding the integration. Okay, so integration of u into v. Okay, integration of u into v can be written as u, keep u as it is, integration of v. Okay, minus so what we do here, we take the differentiation of that u, that means u dash. Okay, u dash into integration of v, that means you have to take double integral over here for this one. Okay, yes, plus take a double differentiation u double dash, again triple integration of v. Okay, this way, and minus and so on. Okay, so we take this one and on this one, so on. Okay, yes, you can take this result or you can apply one more result. So we have one more result for integration of u into v. Okay, that is u into integration of v minus integration of a derivative of u into integration of v. Okay, so you can apply this result also. Okay, both are the bipart rule for solving given bipart function. Okay, yes. Now see that it is one more confusing thing here. Between these two functions, which one is the first and which one is the second function? Whether 1 minus lambda first or cos lambda x is the first. Okay, yes. So we have to think that function very carefully, guys. Okay, we want the function here that once we take the differentiation, that term goes to the 0 or it can be vanishes after some times. Okay, that we have to consider. So we have to be very much careful for this selection. Okay, yes. So for that selection, we also know one more result. Okay, what is the result? That one, ILATE. Okay, okay, not like ILATE in international exam. Okay, it is like ILATE rule to decide whether which function is the first and which one is the second. Okay, I stands for inverse function, EL stands for logarithmic function, A stands for algebraic function, T stands for trigonometric function, E stands for exponential function. Okay, so here we are dealing with the two function. One is a algebraic function, another one is a trigonometric function. So always we consider first function as an algebraic function, then second function as a trigonometric function. Okay, so I'm going to consider this one is the first function. Okay, this one is the first function and this one is the second function. Okay, this one is the second function. So apply integral over first function into second function. Okay, that means integration of u into v. Okay, that means integration of 1 minus lambda, integration of 1 minus lambda into cos lambda x. Okay, cos lambda x d lambda. Now see that, guys, these are the two function different over here. Okay, so this rule I already so many times explained by this rule. Okay, this rule, it is easier to understand now. Let me introduce this new rules to you all. Okay, so this one is the first function u, this one is the second function v. Okay, yes. So keep u as it is. So I'm keeping 1 minus lambda as it is over here. Okay, integration of v. Okay, so we want the integration of cos lambda x. Okay, yes. So what is the integration of a cos lambda x, which is a sin lambda x. Okay, cos has the integration sin lambda x and cos has a differentiation minus sin. So always remember that cos lambda x has the integration, cos lambda x has the integration sin lambda x, and at the denominator we take that differentiation of a lambda x, which is a lambda over here, sorry, x here. Okay, we are taking integration with the d lambda now, so we have to differentiate with respect to lambda. So denominator left here with the value x here. Okay, yes, I hope you all understood how I have taken this one. Okay, that means u into integration of v minus, okay, minus keep as it is, okay. So what u dash, okay, u dash means we have to take the differentiation. One has a differentiation 0 and minus lambda with respect to lambda has a differentiation minus 1. Okay, minus 1. Okay, second I got the u dash as a minus 1, double integration of v. Okay, that means single time integration of this function, and sin lambda x has a integration minus cos lambda x. Okay, minus cos lambda x, and total denominator by x over here. Okay, differentiation of lambda x I written over here. So I hope you all have understood how I have written this one, guys. It is not difficult, just need to apply some basic calculations. Okay, yes. So what do we do in our next step? We take a double derivative of this function. Okay, double derivative means 1 times derivative of minus 1. Okay, that means this one is first derivative, this one is the second derivative, and double derivative we want now. That minus 1, it gives us the differentiation 0. So whatever the terms coming up furthermore here, okay, afterward this, okay, so all gives us the value 0. Okay, so we don't have to worry about that 0. Okay, after that 0. So 1 minus lambda keep as it is, sin lambda x upon x. Okay, sin lambda x upon x, minus minus plus, again minus. So we write minus cos lambda x upon x, cos lambda x upon x here. Okay, now see that, guys, this one is the by part function. Okay, 1 minus lambda sin lambda x upon x minus cos lambda x upon x. So here I'm going to replace this part. This one is going to be replaced over here as we have integral 0 to 1. So they replace this entire part here in this bracket, apply over limit 0 to 1. Okay, yes, let me replace this value. Okay, so what we have here, 1 minus lambda, okay, sin lambda x upon x, sin lambda x upon x minus cos lambda x upon x. Okay, minus cos lambda x upon x. Okay, now see that, guys, I just replace this integral over here. That entire process I elaborated here at downside. Okay, yes. So under this one I explained this one. Okay, so don't get confused. So now see that we have to work on this function here. Okay, so we'll get the final answer for fc of f of x. Okay, this one is our required f of x. So I'm going to apply first limit 1 and then limit 0. Okay, let me take it to the next page. So in our next step I written here this integral under limit 1 to 0. Okay, yes. So now see that we are integrating this function with respect to d lambda. Okay, don't forget it, because while we are replacing the values, we have to think that we are to replace 1 and 0. Okay, yes. So as we are integrating with respect to lambda, so replace 1 as a lambda first and then later on 0 as a lambda. Okay, yes. Now, so if I'm going to replace 1, okay, if I'm going to replace 1 as a lambda, so 1 minus 1, it gives us a 0. If this 0 multiplied by this term, it gives us the value 0. Okay, let me write the next part, 2 by pi, okay, under bracket, this step entire goes to 0. Okay, minus cos lambda x, that means cos x upon x. Okay, minus cos x upon x here, minus cos x upon x, lambda it is 1 here. Okay, yes. So this bracket complete, minus, okay, minus again. So we are going to replace lambda as a 0. So 1 minus 0, it is 1. Sin 0 upon x, that means it is goes to 0. So second step, this gives us a 0. Okay, yes, minus, okay, minus as it is here. Put lambda as a 0, cos 0 it is 1. Okay, so 1 upon x remain here. So bracket complete. I hope you all have understood how I have replaced this upper limit and lower limit here. Okay, yes. So keep 2 by pi as it is. Keep 2 by pi as it is. Okay, minus cos x upon x. Okay, minus cos x upon x, minus cos x upon x, minus minus plus 1 upon x. Okay, yes, this one is the bracket. So see that minus cos x upon x as it is, and minus, this minus minus gives plus 1 upon x. Okay, yes. So 2 by pi keep as it is. Okay, under bracket. So 1 upon x minus cos x upon x. Okay, so what we do, 1 upon x minus cos x upon x, this bracket complete. Okay, this one is our required solved form of the Fourier integral. Okay, I hope you all have understood, guys. It is one of the easy solution, don't have anything difficult here. So for your reference, you can see that as we have given the solve following integral equation, we have to solve that equation using Fourier inverse Fourier cosine transform. Okay, so this one is the example. For your reference, you can refer my entire solution here. So I'm showing that a solution here downside, guys. Okay, so this one is the solution. In my next part, okay, so this one is our required final answer. Okay, you will get this question for 4 to 5 marks in your university question papers. So don't forget it, guys. These are the one of the easy solutions. Okay, so I hope guys you all have understood my entire solution. Okay, so just if you have any doubt, difficulty, let me know in my comment section, guys. Okay, just to make one video, it is lot more effort for me. Just for your single comment gives me a lot of motivation. So thank you everyone. I hope you all have understood my today's lecture. So thank you everyone. Thank you for my today's lecture.